All right, in this video, we are going to move into chapter 2 of the David Lay linear algebra book. And so we're going to kind of move into the idea, talking a little bit more about matrices and maybe a little bit of row reduction, but not near as much as we saw in chapter 1. So we're going to begin this chapter with section 2.1, which is going to discuss some basic matrix operations, some we've kind of already seen before, and then we're going to also look at some different ideas and maybe some different techniques that we want to learn going forward. So kind of relating to the vector talk we did in chapter 1, we want to be able to do, like I said, some operations with matrices more than just using the columns or the vectors of matrices. So when you are working with two matrices, so let's say A and B, as long as they both have the same dimension, which I'm using m by n in this case, then finding the sum, or A plus B, is the m by n matrix whose columns are the sums of the corresponding columns in A and B. So what that essentially means is that, as you can see in my example of my numbers that I picked out here, I've made up a matrix A, which is a 2 by 3 matrix, and I also made up a different matrix B, which is also a 2 by 3 matrix. Since those two matrices match the exact same dimension in this case, we are allowed to add them together by essentially adding their correspondent parts together. So if you double check me here, I'll just circle the first couple. I would start by adding the 4 and 1 together, which is where 5 came from. And then 0 and 1 get added to get 1. And then I'll use a triangle here. 5 plus 1 gives you 6. And you would continue that trend for every element of both matrices to get your final A plus B matrix. The exact same thing is true when it comes to subtraction, in that you can subtract them in the same way as long as the dimensions of the matrix are the same. Now you'll see in my third matrix that I made up over there, my matrix C, and I'll box this one in purple. This is not a 2 by 3 matrix. This is just a 2 by 2 matrix. So thus it cannot be added or subtracted from either of the first two matrices because the dimensions do not match. So that's one operation. The second basic operation when it comes to matrix operations is scalar multiplication. We saw this with vectors back in chapter 1, and it's very similar here. If you have a scalar, and this chapter calls it R, they changed from C for some reason, but if you have a scalar and you have a matrix, then to multiply or to do the scalar multiple of a matrix, which they call RA, is the matrix whose columns are R times the corresponding columns in A. So from that definition, essentially what that means is that if I wanted to find something like 2 times C, it doesn't matter what the dimension of C is. All this is telling me is that I want to take the coefficient 2 and I want to multiply every element of matrix C by that 2. So by doing that, you can see that the top row, 2 times 2 gave me 4, 2 times -3 gave me -6, and so on. So just like vectors, if you want to multiply a matrix by a scalar, it's as easy as just distributing it to every single term. All right. The one big difference we're going to look at in this chapter, or this section, I should say, to begin with, is how do you multiply matrices together when one of the matrices is not just a vector? So in chapter 1, we would multiply matrix A's by column vector X's, and we went over that technique. Unfortunately, that's not going to work to 100% extent in this section. So what I want to cover is let's assume that A is an m by n matrix, and B, here's the key, is probably a different dimension. Let's assume that B is an n by p matrix with columns B1 through BP. Then what this says is that if you take the product of these two matrices and get A times B, this gives you a dimensional matrix of m by p, whose columns would come from A times B1 ... A times B2. All right. So kind of taking that little definition at the top, what this is essentially saying is that when you multiply matrices together, and here's how I've always thought of it. When you put, for example, A times B together. So if this is m by n and this is n by p. Some of y'all might recall this trick if you've worked with matrices before, but the trick says if the inner dimensions match, so in this case, my inner dimensions, if you're thinking like FOIL from algebra, the n and the n match, that tells me, yes, I am allowed to multiply these matrices together. And then what you do is you look at the outside dimensions, which would be m by p, and that gives you the dimension of your final product. So that's usually step one. You should know what you're shooting for before you ever begin multiplying things together. So in my example that I have here, let's assume that A is the matrix 4, -3, -3, 5, 0, 1. And let's assume the matrix B is 1, 4, 3, -2. So looking at my dimensions here, this A matrix is a 3 by 2 matrix, and my matrix B is 2 by 2. So as you can see, if I circle the inner numbers, A and B, they are both 2s. So therefore, I am allowed to multiply these together. And then looking at the outside numbers in this order, this tells me that A times B is going to eventually be a 3 by 2 matrix. So now I know what I'm shooting for and whether or not I get in the right area. So let's write down what we're doing here. You've got matrix A, and you've got matrix B. All right, now from this formula, what it is saying is that you want to take, to find the final columns of AB, is you want to take matrix A and multiply it by just the columns of matrix B. So what this does is this is going to end up giving you your matrix A, which is 4, -3, -3, 5, 0, 1. And we're going to multiply it by just the first column. And then right below it, I'm going to do the exact same thing, but multiply it by the second column. So what this does is that each of these is going to generate a column, which is going to be a column in your final matrix. Now, this should look familiar from what we covered in chapter 1, in that to multiply a matrix times just a vector, you take the first element of your vector, which is 1, and you multiply it by the first column of matrix A. And then you add to that your second entry, which is 3, times the second column of the matrix you're working with. So distributing your constants through, this will give you 4, -3, 0, plus -9, 5, oops, sorry, no, -5, 15, my 1 didn't go through, and then 3. And so down here at the bottom right, or sorry, bottom left for y'all, I'm going to take each of these columns I found and write them in my final answer. So I have just determined that my first column, if I add these together now, 4 plus -9 is -5, -3 plus 15 is 12, and 0 plus 3 is 3. That will be the first column of my matrix A times B. Repeating the process, now for my matrix A times the second column of B, you would take the coefficient 4 times the first column plus the second coefficient -2 times the second column. This is going to end up giving you 16, -12, 0, plus 6, -10, -2. When you add these two vectors together, this is going to give you the second column of A times B. So 16 plus 6 is 22. -12 plus -10 is -22. And 0 plus -2 is -2. And you have just found the final product of AB, which we can now verify from the beginning, did come out to be a 3 by 2 matrix. So that is the official definition way of multiplying a matrix times a matrix. Now, what I'm about to show you on the next slide is that this may not have been the best way of doing it. Now, if this way makes the most sense to you after the next slide, always do it this way. But I'm about to show you what may be a little bit more of a shortcut way, and we can find numbers a little bit faster. in the next part. So what I want to teach you here, and I'm going to use different matrices so we're not just memorizing numbers. I want to show you a rule called, and this book calls it the row column rule. All right. So this is not, we're going to multiply matrices, but we're not going to do the same technique by breaking it down into vectors. So just verifying that I'm allowed to do this. Your matrix A is a 2 by 2 matrix, and your matrix B is a 2 by 3 matrix. Since the inner numbers match, the 2 and the 2, you are allowed to multiply these together, and then the outside numbers tell you your final dimension. So you're going to end up with a 2 by 3 matrix, or you should when all is said and done. Now let's set up what we call the row column rule. 2, 3, 1, negative 5. We are going to multiply that by 4, 3, 6, 1, negative 2, 3. So the reason they call it the row column rule, and here's how I'm going to try to explain it the best I can in this video. We are going to use the rows of the first matrix and the columns of the second matrix to generate our final answer. Now, I already know that my final answer is going to be in a 2 by 3 form. So I'm going to kind of draw a matrix that kind of mimics that form. And here's what we're going to do. And your calculator can help you out a little bit here with all the number crunching. We're going to take the first row of the first matrix, and I'm going to multiply it by each column and create an operation. All right. So for example, if I take the row 2, 3, and I multiply it by the column 4, 1, in my mind or in my calculator, what I am doing is I am taking 2 times 4, first element times first element, plus 3 times 1, second element times second element. And if you compute this, 2 times 4 is 8, plus 3 times 1 is 11. So the first position in my new matrix is going to be an 11. Oops, sorry. Now that you've done row 1, column 1, now you move to row 1, column 2. And I'll do this one more time, writing it out. I'm going to take 2, 3 and multiply it by 3, negative 2. So that would be, 2 times 3 plus 3 times negative 2. Well, if you compute that out, that ends up being 6 minus 6, which is 0. So that's the next number in my top row. And just keep doing this until you run out of columns. So if I do 2, 3 times 6, 3, in my mind, that is 2 times 6 is 12, 3 times 3 is 9, so 12 plus 9 gives you 21. Once you have multiplied the first row by every column, we are then going to go back. Now we're going to focus on row 2, and we're going to multiply it by the same 3 columns again. So I'll do the first one out here on paper, and then I'll do the rest of them out loud. So now we're going to do 1 times 4. Once again, first element times first element, plus negative 5 times 1. And in that case, that's 4 minus 5, which is negative 1. All right. So then we're going to do the 1, negative 5 times the second column. Looks like that's going to give you 3 plus 10, which is 13. And then finally, we're going to do the second row by the third column. Looks like you're going to get 6 minus 15, which is negative 9. And as you can see, this is your 2 by 3 matrix A times B. And so this is the method that is usually preferred, and it's the method that I'm going to do in the rest of the videos when we have to multiply things together. Like I said, if you don't like this way, it's a lot more like kind of visualizing. You are more than welcome to do it this way that we did on number 1, but it is a little more time consuming to do it that way. So as you're working the problems on your homework, just make sure that you're practicing which way you prefer to do it. All right. For example 3, I'm going to change up what I'm asking and see if we can adapt. So the example 3 says, can you find the matrix B if you know that A is 1, 2, negative 1, 3, and AB is 8, 7, 7, negative 2. So what's happening here is that we know that our first matrix is going to be a 2 by 2, and I know that my final product needs to be a 2 by 2. So what you're asking yourself, and I'm going to write it as m by n, you're trying to figure out what dimensional matrix B would make this be true. Well, as we talked about, we know that the inside numbers need to match. So I at least know that the first dimension, the number of rows, is going to be 2. And then if those match, the outside number should give you the dimensions of A times B. So in that case, for the outside number to give you a 2 by 2, your n has to also be 2. So I know that B is going to be a 2 by 2 matrix. Now the problem is going to be is that when I take A, which is 1, 2, negative 1, 3, you've got to figure out what you're multiplying it by. Now you can label this however you'd like to. What I'm going to do is I'm going to do it by columns. So I'm going to let the first column be A1, A2, and I'm going to let the second column be B1, B2. And I got to figure out what those numbers are. Now, even though I don't have the numbers, what I can do is I can do my row column rule to help me set up some equations. Now, how I'm going to do this a little bit differently is that I want to incorporate the same letters in the second matrix when I write out what I'm doing. So what I mean by that is, instead of taking the first row and multiplying it by the first and second column, let's just do the first row times the first column. And that's going to give you A1 plus 2A2. Right? Now, going back to my matrix AB at the top, that should give me the value that's in the first location, which in this case is 8. Now, I don't want to take this same row and multiply it by the second column because that's going to give me a bunch of B's that doesn't help me here. All right. So instead, I'm going to jump down to my second column or second row and multiply it by the first column as well. And that will end up giving me negative A1 plus 3A2. Now, since I did jump down to the second row, this now is going to help me find the first element of the second row of my final answer, which would be 7. And what you've just done is you have set up a system of equations that you can now solve. Now, since this is linear algebra, I know the textbook wants you to set up an augmented matrix here, and you are more than welcome to do that. But since we can do this one pretty quick without doing matrices, what I'm going to do is I'm just going to go back to the old addition method that we covered in the very first video that you probably learned in a basic algebra class. If I were to add these two equations together, the A1s would cancel. You would get 5A sub 2, and then 8 plus 7 is 15. If you divide both sides by 5, you will get A sub 2 equals 3. And if you plug A sub 2 equals 3 back into either equation, I'll just pick the first one, you will get A1 plus 2 times 3 is 8. A sub 1 plus 6 is 8. And you can see that A sub 1 is going to be 2. And so you have just found the A1 and A2 that makes up your matrix B. So that's how you can find the first column pretty quickly. The problem is that now you have to repeat the process to help you find the B elements here. So in purple, I'm going to take those two rows, and similarly, I'm now going to focus on finding equations for B. So if I take the first row of A times the second column of B, you should get B1 plus 2B2. And remember now, back to your AB matrix, you're using the second element, all right? So that's going to give you 7. And then you're going to use the second row of A times the second column of B, and that's going to give you negative B1 plus 3B2. This time, that should equal negative 2. And I'm going to solve this the same way that I solved for A1 and A2. If I add these two equations together, the B1s cancel, and you end up getting 5B2 is now equal to 5. And if you divide both sides by 5, you will get that B2 is 1. Substitute that into one of your equations. It doesn't matter which one. I'll just pick the first one again. So B1 plus 2 times 1 will equal 7. So B1 plus 2 is 7, and thus B1 must be 5. You have found all 4 elements of your B matrix. So for your homework, all you have to do now is write out what your matrix is. So the first column, remember B is up here. Your first column is A1, A2. We found that to be 2, 3. And your second column is B1, B2. We found that to be 5, 1. And that is your matrix B. Once again, I know the homework and the assignments may want you to do row reduction when you set up those equations, and you can do that if you would like, but sometimes in these examples, it may be a little bit faster to just do the elimination method. But if the elimination method becomes too complicated, you can always go back and do row reduction. But that's how you find your missing matrix. All right. So now to introduce kind of how transformations will start to play a role in this. All right. So example 4 says, let the transformation T be a mapping from the second dimension into the third dimension, and let S be a different transformation that maps the second dimension into the second dimension. We are going to define T of X as being A times X, which you already knew. Remember, for right now, transformations are matrix multiplication. So double checking, remember with transformations, the first dimension is the number of columns and the second dimension is the number of rows. So it makes sense that A is going to be a 3 by 2 matrix. And if we let S of X be a different matrix multiplication, now with this dimension, your column and rows match, so it makes sense that your matrix B is going to be a 2 by 2 matrix here. The homework's going to ask you to compute the standard matrix, T of S. So this is where some basic algebra comes back into play. You have to remember what T of S actually represents. That's a compositional function. So this is the way that transformations write it. But what you also may remember is that this is essentially the same thing as saying that we're going to take our S transformation and we're going to plug it into our T transformation. And so what this does is now gives you a notation of T of S. This one most mimics the first equation. All right. So in this first equation, T of X is equal to A times X. For T of S, this essentially means that you are going to end up multiplying A times S. But remember, S is equivalent to B. So this just becomes the matrix A times B. So all this jargon in this problem ends up leading to that T of S is equivalent to just multiplying A times B in this case. So if I take A, which, let me get that matrix down, multiplied by B, let's see if we're allowed to multiply these together. So you have a 3 by 2 multiplied by a 2 by 2. The inner numbers match, which is good. The outer numbers give us our final dimension. So we're going to end up multiplying this together to get a 3 by 2 matrix. So I'm going to use the row column rule again. So the rows of the first matrix times the columns of the second matrix. So let's take row 1 and let's multiply it by each column of the second matrix. So if I do that, 4 negative 3 times 1 3 would be 4 minus 9, which is negative 5. 4 negative 3 times 4 negative 2 would be 16 plus 6, which is 22. Move down to the second row and repeat the process. So second row by first column should be negative 3 plus 15, which is 12. And then second row by second column should be negative 12 minus 10, which is negative 22. And then finally, move to the third row. So 0, 1 times 1, 3 would just be 3. And 0, 1 times 4, negative 2 would be negative 2. And so this is equivalent to the transformation T of S by using our matrix multiplication definitions here. All right, now that we've spent a little bit of time covering matrix multiplication, there are a few properties that I want to run through. Like every other video, if you need to pause during these definition sections, do that and write down what you need, but I'm going to go through and explain each one and then move on to the next slide. So let's assume that A is an M by N matrix, and let B and C have sizes for which the indicated sums and products are defined. So once again, assuming everything works out. If you are going to do what we call the associative law of multiplication, this says that if you want to multiply A times BC, this is equivalent to multiplying A and B together first and then multiplying by C. You probably remember this law from basic arithmetic in that it doesn't matter what order you multiply them in. The biggest difference here is that with matrices, in algebra, you probably could have written it as AC times B. You cannot do this in matrices because you cannot flip-flop the matrices in order, because when you do that, the dimensions may not match up, and thus you can't do it. So it doesn't matter which two you multiply first. It's either got to be A and B or B and C, and then you do your other multiplication step. Rules B and C are called the distribution laws, and really it's just stipulating that left and right does matter in matrices. For example, if you want to multiply a matrix A times the sum of B and C, if you choose to distribute A that's on the left-hand side, then A has to remain on the left-hand side of each multiplication. That way it keeps the dimensions lined up. Versus rule C says if you take a matrix A and distribute it from the right-hand side, then you notice that A must remain on the right of each multiplication. That is set up that way so that your dimensions do not get messed up. Part D is all about scalars, and scalars aren't that big of a deal. This essentially says that if you want to multiply AB by a scalar R, let's say, it doesn't matter whether you multiply the scalar at the end, whether you multiply the scalar by A and then multiply, or whether you multiply the scalar by B and then multiply. All of those will give you the same answer because multiplying by a scalar does not impact the dimensions of the matrices you're working with. And then finally, if you want to multiply a matrix A by the identity matrix, it doesn't matter which side of matrix A you multiply the identity matrix by, because it's always going to give you the original problem. So multiplying a matrix A by the identity matrix is very similar in algebra, regular algebra, to multiplying a number by a 1. It doesn't change the value, but it is something that might show up from time to time. As another note here, if A is an n by n matrix, and this is key because this property only works if you're doing a square matrix, and if K is some positive integer. When I ever mention, and we won't do it a lot now, we'll do it more later, when you raise a matrix to the kth power, all right? So remember back in algebra, if somebody told you to do 3 squared, that's officially the same thing as 3 times 3, which is 9. In matrices, if you have a matrix raised to a power, you cannot distribute the power to each element. It doesn't work that way. Instead, what you have to do is whatever number your A matrix is raised to, you have to multiply A by itself that many times. That is not as simple as just squaring, cubing, fourth powering, whatever it may be. You cannot do that to each and every element. That property does not hold in the matrix world. All right. The last thing we want to cover in this video for matrix operations is the idea of a transpose that we're going to need once in a while. So let's assume once again that you have an M by N matrix A. Then we are going to define the transpose of a matrix A as an N by M matrix denoted by A raised to the capital T, whose columns are formed from the corresponding rows of A. Right? So my easiest way to explain transpose to people is that, as you can tell, the dimensions of a matrix flip-flop when you take the transpose. The rows become the columns and the columns become the rows. And that's how I think of it. You are switching rows and columns. So to kind of show you in a very basic sense of what we're going to be doing starting in the next video is that if this is your matrix, so I've given you a 3x4 matrix A here. So when I ask you to take the transpose of something like this, so that will be denoted as A to the capital T. I know that from my definition, my rows and columns are going to switch. So my dimension should change from a 3x4 ending up to a 4x3. And the way that I usually do this, so we're going to do 4 rows by 3 columns. I do it from rows to columns. That's how I've always done it. I'm going to take the first row of A, and that's going to become the first column of A transpose. So 1, -4, 8, 1. Then I'll do the same thing for row 2. That becomes column 2. And finally, row 3 becomes column 3. And what you have just done for the first time of many times we're going to do this, you have just found the transpose of a matrix. So it's as simple as just saying we're going to flip-flop the rows and the columns here. All right, so no problem here to end the video, but to wrap this video up, now that we kind of know at least what a transpose is, there are a few properties that might help us as we move along for the rest of this class. So let's assume that A and B denote matrices whose sizes are appropriate for the following sums and products. So essentially, as long as the dimensions match up, these properties hold. If you take the transpose of another transpose, you are essentially undoing itself. So as you just saw, our 3x4 matrix changed to a 4x3. If we were to take the transpose of it again, we would get back to the 3x4. So a transpose just undoes itself. If you are trying to add 2 matrices and take the transpose of that, then A plus B transpose will be equal to the transpose of A plus the transpose of B. Part C talks about that scalar again. If you're wanting to multiply a matrix A by a constant R and transpose it, it doesn't matter whether you do the scalar multiplication first and then the transpose, or if you do the transpose and then the scalar multiplication. You will get the same result both ways. The one that does make a difference, and that I see people mess up all the time, is part D. I'm going to do this one in a different color. If you are wanting to multiply A times B and take the transpose of it, that is perfectly fine. But if you're wanting to transpose things first, you have to flip-flop the order. So A times B transpose is equivalent to B transpose times A transpose. So to kind of show you why that property is important, let's assume that A is a 3x4 matrix and that B is a 5, not 5. How about 4x6 matrix? So based on this property, if I were to want to do A times B transpose, all right, well, if I multiply A and B together, you see that the 4s match and you're allowed to do this, and then the A times B would end up being a 3x6 matrix. If you take the transpose of that, it becomes a 6x3 matrix, and that's what A times B transpose. But let's assume that you forgot to flip-flop when you distributed it in this idea, all right? So if I were to do A transpose B transpose, which I know should not be right, the transpose of A would be a 4x3 matrix, and the transpose of B would be 6x4. As you can see, these inner numbers don't match, and thus you cannot multiply those together. So that's why this one doesn't work. Versus, let me go ahead and show you while we're here. If I were to do B transpose A transpose, the transpose of B would be 6x4, the transpose of A would be 4 by 3. And since the inner numbers do match, you are allowed to multiply them, and the outside dimensions give you your final result, which is 6 by 3, which is the same as it was the first time I did it. So if you choose to use this last property, just make sure that you're flip-flopping A and B before you do that. So that ends my video on section 2.1. We kind of went over the basics of matrix operations. We have seen elements of some of this stuff before, but this kind of starts letting you see the bigger picture where we're going to be doing multiple matrices at the same time, and we need ways to put them all together. In the next video, we're going to move into section 2.2, which we're going to introduce another matrix operation called the inverse of a matrix. It's a little bit different, so it's in a separate section, but we'll talk about that next time.